Hello, everybody. Today we will be looking at searching and sorting. So, these are two common operations that are done on arrays or lists in various programming languages. And it's more of like a concept of computing itself rather than Python. So, we'll just be looking at the implementation of these concepts in Python. But firstly, I'll explain what they actually are. So, first I'll just go on with the difference between searching and sorting. So searching is like when you have a target element and you want to look for it inside of an array, you use a searching algorithm to look for it and point it out or pull it out from the array. A sort is like when you have like a jumbled up array and you have to like organize it into order. So that uses different algorithms. And there are several algorithms for either of these operations. So we're going to be looking at binary search, sequential search, bubble sort, and merge sort today. So first, let's start with the simplest of all of them, the sequential search. So a sequential search is like when you have a jumbled up array and you want to look for one particular item. So you check each and every element of the array until you get to the end to look for the item. So like, for example, as you can see on the screen, you have 73 and 12. Maybe our goal, we had to get 38, and like, is this 38? No. Is it 38? No. So like we go on each an element on and on until we get to the result as 38. So the program for this is comparatively simple, but the problem with this is like if the desired element is at the end, it takes a really long time for the computer to find it, which also causes more load on the processor. So it's really computationally heavy if you look at it that way. So we'll just look at the actual program for this here. So first in the comments we have time complexity O(n), which n is the number of elements in the array. So this notation O(n), it represents like the maximum number of time, like relating to like the worst case scenario if to fully search the array. So the worst case scenario is equal to the length of the array itself. If the desired element is at the end, it has to travel to the whole length to search for it. So the time complexity is O(n), and the space complexity is O(1) because it only uses a constant amount of extra space. It doesn't need temporary arrays and stuff. So the space complexity is O(1). So the program is really simple. So for each index, for elements at each index, we just check if the current element is equal to the search target. If it isn't, then we just move on to the next one. So when the desired element is found, we just send a print message to the screen to inform the operator that their desired element has been found. So I'll just play this program to show you. So the first search target is 22. So it had to check through 39 indexes and do 40 comparisons to get to this result. The next search target was 59. It had to do 32. It had to do 33 comparisons at 32 indexes to reach the result. So you can see that this is like a pretty simple program. So you just have to compare and compare until you find the result. Then you just print it and you stop the program. So binary search is quite different to this because this in this you require an ordered array before you search. So the logic in this is that you compare this desired element to half at like the midpoint of the array. If it's bigger than like if the I don't know if the desired element is like 95 for example, then you go in the middle of the race, like this between 49 and 51. Then you compare 95. So is it bigger than 49? If it's bigger than 49, it's going to be in this half of the array. Then you take the midpoint of this half, so like the quarter essentially. So like around somewhere here. So is it bigger than 81 or 83 or something? So if it's bigger, then you take like a half of that. Then you take the midpoint in this array, and you repeat this process until you just get like two pieces, and just get like two arrays like this. At this point, you can at this point you can just directly compare one of them because it's either going to be this one or this one. The thing is, this process is a lot faster because the number of comparisons depends on log, like log to the base 2 n, because just split it up into halves and you just search in each half. So, but the problem is this requires the array to be sorted beforehand, otherwise it won't work. So let's look at the code here. So left index and right index. So left index is 0 and right index is the last element. So you take the midpoint and you say it's middle index, and you compare the target element with the middle index. Then if it's smaller, then you reset the start index. If it's bigger, you reset the end index. Then you do the comparisons again. You keep on repeating it until it directly equals the target element. So the target element 1 is 57 and target element 2 is 82. So let's run the program and see. So since the first search index was 57, it checked if it's bigger than 49. If it was, then no need to check with the smaller numbers because it can be bigger than them anyway. So you check through this. This list is the same as this one. So next, we check with 75. Since it was smaller than 75, you split it into half again. It's going to be in this part, which is the same as this. Then you do the same thing again. You compare it with 61, which is the midpoint of this half. Then, if it's smaller than that, you check it in this array, which is the same as this one. Then you compare it with 55. If it's bigger than 55, it's going to be between these two. And it compares between these two, the same one is here. Then it just directly matches the 57 with 57, and you just stop the comparisons. For the next one, it's the same process. It's been repeated again. Well, the difference here is that the desired element is actually not inside the array, which gives us a result of -1. So the process has been done like the same as the one we've discussed before until it gets to 83 and 85. Then it compares 83 with 82 and is smaller, but the smaller numbers in 83 are already been filtered out. So 82 is not present in the array. So the comparison has been stopped. And the result for target is given as -1 to represent that it's not present in the array. So in like really large data sets, binary search is more often used than sequential search. But now let's just move on to sorting. So first let's do bubble sort. So in bubble sort, the process is that well, you start with the first element in the array. So if the first element is bigger than the second one, you swap them. Then you check the second one with the third one. If the second one is bigger than the third one, you swap them. You do this process repeatedly until the end. Then you keep on repeating it until no comparisons are made. So here's the code for that. You can have a look at the code. So the thing is, in bubble sort, you can't just sort the whole array with one pass. You have to make multiple passes of comparison. So in pass one, we had to sort this array. So like 34, 64, 25. To okay. 64 is bigger than 25, so that's swapped. Then 64 is bigger than 12, which swapped. So they swap together. Then 22 and 64 swap. 11 and 64 swap. Then the sixth step, it just rechecks if there's any need to swap anything between 64 and 90. So the pass one ended. So for pass two, we go back to the start and check again. So 34 is bigger than 25, so they swap. 12 is smaller than 34, so they swap. 22 and 34 swapped. 11 and 34 swapped. And that's the end. So in step 3, we go back to the start again. So 12 and 25 stop, 22 and 25 stop, 11 and 25 swap, and that's all the swaps here. So pass 3 ended. Pass 4, 22 and 11 swapped, then nothing else swapped, so the pass 4 ended. For pass 5, 11 and 12 swapped, they were not in the right order back there. So pass 5 ended. In pass 6, it just checks again, but the array is already sorted, so it just stops. So the final sorted array is printed over here. There are also many more types of sort algorithms, but I'll cover them at a later date. So let us now move on to merge sort for now. For merge sort, the thing is the array is divided up into two parts. Then each part is divided into two parts again and again until each sub-array is just one element long. Then each of these sub-arrays are just compared with each other and put in order. Then they're assembled together again. So the time complexity is n log n for all cases, worst, average, and best. Space complexity is O(n) because you have to make temporary arrays to need to be merged together. So I'll just play the code here to show you. So the original array was 64, 34, 25, 12, 22, 11, and 90. Then the array is split. So this array is split in half, so it becomes three elements, then just like 1 and 2. Then this group of 2 is split into 1 and 1. So merging arrays 25 and 34. So it puts them in order. 34 was before 25, now it's after. You can see it here. 64 and 25 and 34. So 64 just comes at the end here, in this case. Then the other half of the array from this part, this is split. It goes 12 and 22 and 11 and 90. 12 and 22 were already in order. 11 and 90 were also already in order. Then these two are compared with these two, so 11 comes before, then 12, then 22, then 90. Then the same thing that was done in this part is done with these two arrays. So they're also put in order at the end. So the final sorted array is 11, 12, 22, 25, 34, 64, and 90. So the thing is, merge sort is way more efficient than bubble sort because bubble sort requires more comparisons to take place, which is like really heavy. But in small data sets, there's not really that much of a difference. The difference only occurs in like larger data sets where you can see a noticeable difference in time. So that's the end for today, and see you soon.